My name's Austin Pleasance. I'm a product engineering manager here at Q-PAC. Been here almost 4 years next week. Started out as a mechanical engineer, then did some electrical engineering work, and then some applications. Been a little bit all over the place on the engineering side. So hopefully that makes me qualified to talk to you all about efficiency. It's a little bit of mechanical, a little bit electrical. So I'm gonna talk about a little just high level EC versus AC, some system versus motor efficiency and the differences and when you should care about each one of those. We'll explore FEG and FEI, and which one of those you need to worry about, and then we'll end with harmonics and how we can deal with those harmonics. All right, so this is the most blanket statement of all time, but EC motors are approximately 30% more efficient than AC motors. There's like 150 different caveats there to that statement, but in general, if everybody wants a rule of thumb, everybody wants something they can just...
Everyone wants a quick...
Exactly. So about 30%. The main difference between EC and AC when it comes to efficiency is the turn down. When, can't remember who was talking earlier, I think it was John, talking about the AC motors and the turn down. This blue line here, when you turn the AC motor down from its nominal rotational speed, the efficiency is going to plummet. It's really going to drop off quite a bit when you're turning down away from that maximum speed. EC motors, that green line, are going to stay right about that same efficiency throughout the full operating range of speeds. All right, here is a performance curve of one of our plug fans. Can anybody tell me where on this curve would be the maximum efficiency point? So we're looking right about there, a little bit lower. So that's going to be about your maximum efficiency point, and it'll follow a trend somewhat like this. Not exact. I drew this in paint, so don't look too closely. But somewhat like this. The further away you get from the maximum efficiency point is where the efficiency will drop off. So if all you're worried about is efficiency, then you're going to want to pick something close to that point. But I'll go into a little bit more detail later why that might not be the best way to select systems. Now I'm going to talk about system versus motor efficiency. So when you have a fan system, an old belt-driven fan system with a VFD, there's a lot of places, a lot of opportunity for losses. You have a lot of different mechanical and electrical components working together, and each one of those is going to introduce some sort of... So the belt, the drive, the bearings, those are all different places where you can lose out on what your maximum efficiency could end up being. So if you have an old rusty shaft and rusty falling apart bearing, your efficiency obviously is not going to be as good as a brand new bearing, right? So sometimes when people look at an old system, they look at the old spec sheet for the motor, find a data sheet somewhere that's probably like hand drawn maybe. Sometimes these things are so old, but they see a motor efficiency and they say, okay, the existing motor is 55% efficient, for example, right? And then they go into Quips, our selection software, and they design a new Q-PAC fan system, and we spit out something that is 50% efficient. And they say, hang on a second, how can this brand new technology, EC, everything's supposed to be more efficient, how can that be less efficient than my existing technology? And the reason is they're not comparing apples to apples. They're comparing system efficiency to motor efficiency. So what we report in Quips is a total system efficiency. So when you're comparing efficiencies, you want to make sure you're talking the same language and comparing the right numbers. So the motor efficiency does not take into account any of the losses of the belt, the drive, everything else. You want to look at the total system efficiency to compare it to the Q-PAC to see how much more efficient we really are going to be. Anybody know what FEG stands for? Fan efficiency grade. There we go. Teamwork. So fan efficiency grade is a measure of maximum efficiency of a fan wheel. So we're looking at just the aerodynamic efficiency of a wheel, and has nothing to do with the motor, has nothing to do with the actual operating point that you're operating at. It's only going to be the maximum that wheel can ever be. So, and it does not account for part load efficiencies either. It's just going to be at 100% RPM, at maximum efficiency point, what is the efficiency of that wheel. So everything used to be about FEG. That was what a lot of regulations were built off of. In the state of California, your FEG had to be at least 45 or 50, I can't remember what it was, but everything was based off of FEG. And I put this slide in here to highlight why that didn't really make much sense and why we moved on from FEG into FEI, which I'll talk about in a little bit. But this wheel here, you can see there's a lot going on here. Some engineer spent a lot of time designing this wheel, they did what's called biomimicry, where they took the apparently the humpback whales are like really efficient swimmers in the water. They can travel way further than they should be able to based on their geometry, and it's based on, the scientists think it's based on the shape of their fins. And so they took some inspiration from that and designed the fins, the blades on here after the humpback whale fins to gain some extra efficiency. And they're just trying to eke out every % of efficiency out of these wheels. Side note, the leading edge of these blades are shaped after an owl's wing, because owls can fly through the night very quietly, and you want your fans to be quiet, right? So the leading edge is designed the same geometry as an owl's wing to make them quieter. But anyways, this wheel has a really high FEG score. 85 is like the highest I've ever seen. Really high FEG score. But if you apply it in the wrong spot, like 6,000 CFM at half inch static, for example, that efficiency is going to be less than 40%, which is not good at all. So that's why FEG has kind of been phased out, because it really depends on how you're applying those. We're just talking about purely the maximum efficiency it could ever be with FEG. So you might know what FEI stands for. It's a little buzzword. There you go. Fan Efficiency Index. So Fan Efficiency Index is a measure of wired air efficiency compared to a baseline fan. So we're taking what ASHRAE has determined to be at each operating point. They say, okay, at 6,000 CFM, at 6 inches of static, you should be consuming X amount of power. And we're comparing that power in the actual system to that baseline that they've determined.
ASHRAE determines the baseline? Okay.
Yep. And so it's the baseline fan divided by the fan power, so the larger the score, the better. So state of California, for example, has an FEI limit of 1.0 right now. Everything has to be above 1.0 in the state of California. And why should you care? So the DOE, Department of Energy, has adopted FEI as the new metric that matters the most. And by 2029, they're going to require for our types of fans to have an FEI score of at least 1.35, which is terrifying for a lot of companies, but luckily we have this really awesome technology that already has really high FEI scores in most applications.
So they even sell it, manufacture it?
Yeah, so we will not be legally allowed to sell a system. If you tell me your operating point is up here, I could not sell you the system. So.
It's still at one point?
What?
It's still at one operating point?
Yes, so this the FEI is at the specific operating point that you're designing it for. Technically, you would not be allowed to operate it outside of those zones either, but I don't know how they're going to enforce that. But yeah, whatever the design point is has to meet this 1.35. Right now, the year is 2029, but who knows with elections and government and yeah. And I'm sure it'll come in California way before that. They're notorious about immediately enacting whatever future laws are going to come. So, yeah, so that's why you should care about FEI. This graph here is one of our plug fans. I know the numbers are really small, but everywhere in the wouldn't meet this new regulation. Everything outside of that would not meet the 1.35. One thing I want to point out here is if you recall back to the maximum efficiency point that I was talking about earlier, if you notice, it's not the same as the maximum FEI point, right? So the maximum FEI point is actually going to be way down here. But you're never going to design a system down there, right? That's way more fans than what you need, way more horsepower than what you need. It's going to be super expensive, take up a lot of space. You're never going to design down here. But the main point is we would like to encourage people to get down off of that maximum RPM line for several reasons. But your FEI is going to increase if you get down off that maximum RPM line. You don't want to be right on the cusp. Obviously, sometimes you have to in order because of space constraints and other things. But if you can get down off that maximum RPM line, your FEI is going to go up. Your total energy usage is going to go down, and the life of the motors is actually going to be drastically better. So it's actually exponential, the life expectancy of the motor. When it's an exponential relationship between the duty of that motor. So if you're running at 100%, it might last 1 year. I'm just making numbers up right now. And then at 90%, it would last more than double that. and then at 80% it'll last like 4 or 5 times that. Like it's exponential as you turn down off that 90 less than 90% load. So again, FEI shows how good a fan system is at the operating point, and FEG just shows you how good it could be. So that's why we've shifted from one to the other. I don't know if anybody of y'all sat through Christian's harmonics presentation. Hopefully y'all learned something from that. I'm not going to go into as much detail about what harmonics are, but I'll explain a little bit about when you should worry about them and what our potential solutions are. So some rules of thumb to when to be cautious. So we found out that our technology is going to produce a similar amount of harmonics to a 6-pulse VFD. So if there's an existing 6-pulse VFD that you're demoing out and replacing with the Q-PAC system, most likely you're not going to need to be concerned about harmonics. If that drive that you're replacing is an 18-pulse, 12, 18, then usually the building put that there because they were having harmonics issues before, so they went with a low harmonic drive previously. So, and our system will then generate more harmonics than what they have now. So generally, if you see an 18-pulse, then you should be alert and be thinking about potential harmonics mitigation solutions. Another obvious one is replacing a linear load with a nonlinear load. I don't see too many of those anymore. Pretty much every fan we're looking at now has a VFD already, but there still are some out there without VFDs, and in that case, harmonics are going to be more than 0 harmonics. So, and then systems above 100 amps. So harmonics are all a ratio. So if you're on a 1,000 amp circuit and you have a 20 amp load that's pumping in harmonics, it's not going to be a big concern. But once you get over 30, 40, 50% of the total circuit that has harmonics on it, then you're going to start seeing some nuisance fuses tripping, some buzzing sounds. You're going to get some heat build up. You can have a 100 amp fuse that blows at 80 amps because it just heats up and degrades that fuse. So generally, a 100 amp fuse would blow at 100 amps, but you could have it blow much below that if there are harmonics. I know harmonics are a big buzzword and everybody's scared of them, and rightly so. There are some major concerns if they're not dealt with properly, but the good thing is usually it's not an issue. Historically, 1 in over 1,000 Q-PAC systems have had issues with harmonics. But if you do see some of these warning signs ahead of time, it's much better to be proactive about it than reactive later. So yeah, that is one of the potential solutions. It's not solving the problem of the harmonics, but it is treating one of the symptoms, and will usually get people by. Our largest panels, starting in December, will have built-in circulation fans already from the factory, so you're not having to retrofit a PC little computer fan solution or something like that. But if we do identify some of these warning signs ahead of time, there's a couple things we can do. We have passive and active filters. I think Christian talked about the differences between those, so I won't go too into detail, but we have TCI is our main one for passives. We're looking at some other ones as well. Actives, we have the Zeal, and we also have Schneider for really large ones. So like, I think the largest one on that job was going to be it was going to be way bigger than what Zeal could provide. So those are like almost refrigerator sized filters with fancy touchscreens, and passives are usually pretty easy to apply. We can help you size those if you have those warning signs. We'll help you size the filters and figure out which one's the best option to go with. Obviously there's a price difference and lead time and all that stuff, but yeah, and then I just want to go through some of the other ways we define efficiency here at Q-PAC. So this whole time I've been talking about motors and electrons and things like that, but there's so many other ways that Q-PAC is very efficient. The first thing is with quoting with our selection tool Quips. You can get a quote instantly, y'all know that, but it really is a huge deal for us to be able to have the drawings provided instantly. You're not waiting on an engineer to draw something up, unless it's a special, but you're not waiting for an engineer to draw something up. You have the drawings there instantly that you can download, and you have an instant price as well. So we like to believe that's a pretty efficient process. You saw the install during lunch, how quick it is to install. We spent 6 years plus of just obsessing over every screw, every harness, every plug, every label to make it as efficient as possible during the install process. It took 38 minutes, obviously an ideal situation, but 38 minutes to do that install during lunch today. Maintenance is also super efficient. We want the plug fans to be as swappable as possible. That's why we designed the plugs and the everything that went behind that. And then the last thing is new product design and programmers. So Matt came up with this term called programmers, where every engineer at Q-PAC is accountable for the physical and the digital representation of the product. So every engineer at Q-PAC can write code and is accountable for code. And the person who is designing the bulkhead wall that has the logic for when it's greater than 150 inches, we need to split it into two, or if it's greater than 120 inches, whatever, then we change the channel size and add a screw hole here, add a screw hole there. All of that logic is defined by the mechanical engineer and written in the code by the mechanical engineer. We eliminated this feedback loop between engineering and software, where it used to be like a game of telephone almost, where engineer sets the requirements, passes off to software, they go away, code it, come back, and it's not at all what the engineer wanted, and it really stifled our agility and speed in new product development. So that's why Matt is so big on programmers and making sure everybody is accountable, both physical and digital representation of the product. So it really allows us to pump out new products way faster than we would be able to otherwise, and that's really the secret sauce behind the instant quoting and instant drawings in Quips. So yeah, that's pretty much all I got. Hopefully you understand the efficiency of Q-PAC.